It's this slide, molecular geometry. So, this lab that you're doing is a molecular geometry lab. So we're skipping over some of the other concepts, and we're going to talk about this a little bit. The way that a substance behaves, its melting point, its boiling point, whether it's a gas or a solid or a liquid at room temperature, is all determined by its molecular geometry. And if we have something like my little friend, hydrogen cyanide here, we have some degree of molecular polarity. What that means is we've got an area of charge on the molecule. This happens, oh, and my little friend Mickey Mouse is not up here. Mickey Mouse is what? Water, yes. So when we've got something, either that's got unshared pairs, such as this, or has got a real serious difference in electronegativity, hydrogen to nitrogen, fairly significant, you're going to end up with an area of charge on the molecule. That's molecular polarity. When we go, so we've got these neat little model kits here, and they are neat, they're fantastic, they're lots of fun. Imagine if you bought a few for home use. But they're, well, and actually if you take chemistry in college, you can purchase these simplified versions of them. And if you're taking organic chemistry, so if you're going into medicine, pharmacy, anything like that, you typically want to pick one of these up. Don't buy it at the college bookstore, it's a ripoff, but find them online. Because in organic chemistry, it really helps to be able to visualize your molecules. So, figuring out how these things are shaped, how they're structured, is not, it seems really easy because, well, the holes are in the right places. But we haven't always known that. So figuring out how a model should be constructed, figuring out what shape a molecule is going to have, has been a process of experimentation and model making, lots of model making. So, we have this thing, we pronounce that Vesper theory, even though it's clearly Vesper. We usually say Vesper theory. It stands for valence shell electron pair repulsion. What it means is electrons don't like other electrons. That's as straightforward as we can get. So if we look at this little ammonia molecule right here, we've got 3 hydrogens. These white pieces represent hydrogen. And we have this paddle representing an unshared pair. These hydrogens, well, I should say, protons don't like other protons, electrons don't like other electrons. These hydrogens are essentially a what? They're a proton. They're just a little naked proton hanging out there. They're sharing electrons with the central nitrogen. These hydrogens want to be as far away from one another as is possible. So this one swings over until it's equal distance between the other two. Okay? You end up with this nice symmetry. Well, there's a problem though. These electrons are going to repel the electrons that are being shared between the hydrogens. So these hydrogens want to be as far away from one another as possible because their little protons are repelling one another. The electrons that they're sharing, that are in their orbitals, are also being repelled by this thing. So it wants to be as far away from everything else as possible. So what we end up with is a situation where everything spaces itself out to be as far from everything else as possible. And that determines our geometries. So what this means is that if we have a diatomic molecule, what does the prefix di mean? How many? 2. So an example would be a hydrogen molecule, H2. They are going to be as far apart from one another as possible, which is in a straight line. Okay? If we have 3 things together, it's going to be linear. It doesn't really much matter what they are. That's as far away as from one another as they can get, which is in a straight line. If we have 4 atoms, oops, I gotta find my trigonal planar here. if we have 4 atoms as far apart from one another as they can possibly get, here we go, is what we call trigonal planar. So trigonal, what shape do you think that relates to? A triangle. What does planar mean?
Flat.
Plaid? No.
Flat.
Oh, flat. Yes, plaid? No, that's an odd association. Yeah, flat. In a plane. So we have trigonal planar molecules look like that. Everything is arranged in a triangle, and it's in a flat plane. Now, if we get 4 things, we get what we call tetrahedral arrangement. And if you've ever played jacks, these are not jack-shaped, but they're similar. No matter how we throw this thing, one point's going to land up, right? This is a tetrahedral arrangement. Now let me ask you this. If we replace one of those with an unshared pair, it's the same arrangement, but this is no longer tetrahedral. Now we have this little pyramidal structure, where these things are bent down by the force of this unshared pair, but they're still arranged in sort of a rough triangle. Okay, so we'll get into more of that. This is where we get into the unshared pairs. So if we've got an unshared pair on a central atom, which is the case in this, and this is NH3, this is ammonia, the unshared pair will repel everything else just like the regular other atoms attached to the central would. So this is where we get bent geometries, and I should have had my water constructed here. So water has only got one oxygen, one oxygen, 2 hydrogens, right? So linear, yeah? Except we know it's not linear. Why is it not linear? Well, it's not linear because oxygen, that central oxygen, has got 2 unshared pairs. And they force those hydrogens down. So we have what we call a bent arrangement. So if it weren't for these unshared pairs, this would be linear. These would be in a straight line. Because that's as far away from one another as they can get. But because of the fact that we've got these 2 oxygens, or these 2 unshared pairs on the central atom, these things bend up, and we have a different shape. So you have to consider unshared pairs when you're thinking about geometry. Now, unshared pairs on non-central atoms don't change geometry. The geometry is changed by unshared pairs on the central atom. Okay. We have this thing called hybridization. We will talk a little bit more about that tomorrow, but what I want you to be aware of is terminology. So if you look at your lab packet for a moment, you bring the lab packet back with you, I hope, and ask you to. If we look at the lab packet, the first column on that first page, number of lone pairs on the central atom. So that's those unshared pairs. So let's do this one together. This is water, H2O. How many unshared pairs are on the central atom? 2. And the next column is total number of effective pairs on the central atom. That's how many things are bonded to your central atom. So how many things are bonded to the central atom here? 2. So then we look at arrangement of electrons based on number of effective pairs. It's sort of a code thing we use. A is your central atom, so there's always going to be an A. B with a subscript for how many things are bonded to the central. So this would be A, B2, this is water, and then E for how many unshared pairs you have with a little subscript. So this would be A, B2, E2. We'll practice more of these and you'll get better at them. So because this has got 2 atoms bonded to the central atom and 2 unshared pairs, this is an A, B2, E2. Okay? we will finish talking about the geometry a little bit later. So, okay. We'll talk more about hybridization tomorrow. We'll stop it there.